SQL Server provides three types of indexes: a clustered index, a non-clustered index, and a full text index. The clustered index effectively sorts the data in the order of the clustered index. This is not 100% true, however, it is close enough to true that you can count on this from a performance perspective. Because we can only physically sort the data in one order, the rest of the indexes are going to be non-clustered. It says here full text is discussed in a later section. That's part of the class. We will not be talking about that today. Don't worry about that too much. What we are going to do, though, is spend, a good solid 10 or 15 minutes going back and forth across these next two slides. If I've put anybody to sleep, this is a great time to wake up. This first picture depicts a clustered index on last name. First, let's talk about how the index structure is built. As we're looking at this, what we do is we say, okay, in this data page level, we are going to physically sort the data. So we are actually physically sorted here by last name. Now what we're going to do is we're going to take the first entry from each page and put that in the intermediate page. So the first entry from the first data page is Albert. The first entry from the second data page is Brown. First entry from the third data page, etc., gets brought into these intermediate pages. Once we've got the intermediate pages built, we continue building index levels with an entry per page. We will continue doing this until we get to the point where the index level has only one page in it. That is called our root page. Our root page is where approximately 99.99% of all of our access gets done, and that's on a good day. Now let's find something using the clustered index. Let's find Joe Baker. Baker is between Albert and Jones. We follow the Baker pointer down. Baker is between Albert and Brown. We follow the Albert pointer down. Now we're on the data page. Oh, there's Joe Baker. What's our cost of bringing back Joe Baker? We had to read in the root page, we had to read the intermediate page, and then we had to read the data page. So effectively our cost is 3 page requests. Now let's come down to the non-clustered page. We'll be coming back to that in just a minute, by the way. We've already got a clustered index on last name, so we've already physically sorted by last name. What we need to do now is ask ourselves, what if I want to bring back all the Jeffs? What if I want to bring back all the Jims? What if I want to bring back all the Amy's? In order to do this, what we want to be able to do is have an index so that we are not doing an index scan on last name, first name. Here, I'm creating an index on first name. Now, because I need an entry for every single row of data that I want to find, I will have an entry in the leaf page for every row of data. 20 million rows, 20 million entries in the leaf pages. Now, once I have that large number of leaf pages, I build the intermediate pages in the non-clustered index the same way I did for the clustered. An entry per page until I get to the root page. Because the leaf level of the non-clustered index is so much bigger than the leaf page of the clustered index, which is actually the data page, the non-clustered index structures tend to be much larger than the clustered index structures. Don't let that dissuade you from creating an index. So, let's go find all the Amy's. Amy's between Amy and George, we follow the Amy pointer down. Amy's between Amy and Bob, we follow the Amy pointer down. Now we're on the leaf page. We have 2 Amy's. What I need to do once I get to the leaf page, I still need to make a request to bring back the pages that have Amy on them. So here I have 2 Amy's, I make 2 page requests. A single random row retrieval, meaning I have a specific row I want to bring back, whether using a clustered or a non-clustered index, the non-clustered is going to tend to take 1 I/O longer. But unless you're doing 100,000 of those a minute or 1,000,000 of those a minute, you're probably not going to be able to measure the difference much. But let's think about this. What if I have 50 Amy's? If I have 50 Amy's, I read the root page, I read the intermediate page, and come down to the data page. Let's say all 50 entries are there on the leaf page. I still have to make 50 page requests to bring back all the Amy's for 53 page requests. Let's come back to this clustered index. What if I have 50 bakers to bring back? I have the 3 pages to get down to the data page. On a good day, I may have all 50 bakers on the same page. I have an 8K page. If my rows are 100 bytes wide, I've got 80 rows per page. If not, I can read the next page. I'm sorted in name order. I can just go there. 3 to 4 IOs to get 50 bakers, 53 IOs to get 50 Amy's. As you start increasing the number of rows that you're bringing back with that non-clustered index, the cost of the non-clustered index gets very high. Some of you are probably already a step ahead of me. What happens then when we're using this non-clustered index to handle our joins? Well, guess what? If I have a non-clustered index on my foreign key and I've got an invoice header and an invoice detail, what happens when I go from the invoice to the detail? Well, if I've got 50 50 invoice detail rows, I need to make 50 page requests to bring that invoice back. What would happen, though, if I had a clustered index on the foreign key in that invoice detail table? Now, all of a sudden, my index retrievals, my index detail retrievals are 50 times faster. I'm literally doing it with 1 page request instead of 50 page requests. I can't tell you how many times I've simply changed a non-clustered index to a clustered index and gotten incredible results. Think about it. That's a 1-table join that suddenly got 50 times faster. If you have a 3-table join, you have invoice header to invoice detail to addresses. It might become 50 times 50 times faster. So by changing your non-clustered indexes to clustered, it might suddenly be 2,500 times faster to bring the data back. I have experienced multiple occasions where changing index types, even when we had good matching indexes, made longish reports, invoice runs, customer bills, payments, runtimes go from multiple hours to a few seconds. And you really don't believe it until you see it, but if you look at the way the indexes are put together, it becomes really obvious what the optimizer is and is not able to do, and how much extra work it's got to do depending on the type of index that you pick. So the clustered index tends to be 1 IO faster because it tends to have fewer entries in it. They're great for ranges of data. They're great for order bounds. The non-clustered are a bit slower, take up a lot more disk space, but are frequently the next best alternative to a table scan. Frequently the next best alternative to a table scan. Let's think about that one for a minute. Here we talked about just 2 Amy's, but let's take a different situation. Let's say we've got 10 million entries in this table, and let's say we're at an Amy convention. At this Amy convention, half of the data are Amy's, and half the data are Amy's friend, Amy's significant other, whatever is the politically correct thing to say there. We've got a database which is half Amy's. Now, if we put a non-clustered index on Amy, what happens? Well, 10 million rows, if we're fitting 100 rows per page, that gives us about 10,000 pages of data. So the cost of a table scan is about 10,000 rows. What if we use the non-clustered index to find the Amy's? Well, if we have 500,000 Amy's, we have 500,000 page requests to make. 500,000 page requests for using the non-clustered index, 10,000 page requests to do a table scan. 50 times faster to do the table scan. Well, guess what? The optimizer is going to go ahead and do the table scan there. As the number of rows you bring back changes, the usefulness of that non-clustered index reduces, and your chances of using a table scan instead are going to increase. For some queries, covered queries, non-clustered indexes can be faster than clustered indexes. This is an exception to the rule. Let's go back and look at this page again. Let's go back to our prior assumption and say, well, we fit 100 rows per page. We're fitting 100 rows on an 8K page. How many keys are we fitting on a page? Well, if we have an average of 6 characters for a first name and a few characters for overhead, we may fit 800 to 1,000 entries on that leaf page. What does that do for us? Well, what if my question is, how many Amy's have I got? The answer to the question, how many Amy's have I got, does not require me to go to the data page to pick up the row. Instead, I can just go from the root to the intermediate to the leaf and pick all the information up off the leaf. In fact, if I have multiples there, I can walk those leaf pages and pick up all the Amy's, just like it's a clustered index. This is a cool trick. It's been around forever. Forever being, well, I've been doing this since the late 80s, so 25 plus years. This has been a relatively common trick. But what's happened is, as you take a look at this trick, what it occurs to you is, every time I want Amy, I also want her phone number. So you bring the phone number into the index. Well, that doesn't really cost you much. And all of a sudden, you can bring up all the Amy's with their phone numbers in a heartbeat. What happens, though, as things move around, or as things change, you realize that if that's in the index structure and it is a volatile column, and you're not sorting by it, you're never going to say, give me all the Amy's order by phone number. That's just not something you're going to do. You don't need to sort by phone number. If the telephone number is a volatile, Amy's got a throwaway phone and she always has a new telephone number every month. Do you want to go move that Amy around physically just because the phone number changes? What we can do with the onset of about SQL 2005 is an include column. The idea behind the include column is we have the ability to bring the information back into the index structure without sorting on it. That gives us effectively a new clustered index and a smaller clustered index. That technique is called index covering. It's brilliant, and you should use it.